as he said, my name's Doug Oucharek. I'm the manager of the Lustre Development Group at Intel, and I'm, as introduced, here to talk about Lustre, focusing in on how Lustre uses OFED and the fabric associated with OFED. And I want to go over things like the usage patterns of how we use it, and then start pointing out some of the pain points we have now and the pain points we're going to have in the future as things start to go towards exascale. And put out, well, what I call here requirements, but let's just say it's our wish list, things that we would really like to see from the fabric community to help us keep Lustre moving forward and doing what it needs to do. Just to point out, at the end of these slides, I summarize all my wish lists, you might say, on 2 slides. I won't go over them, but if you download the slides after my talk, you'll be able to get a nice little executive summary that you can take away of things that we would like to see. I'm going to take a bit of a new approach here. Normally, in these things, we talk about network stacks, we look at code, and we start looking at the wire, and we get really down to the nitty-gritty things. I mean, we're engineers, our hearts are in that area. But I think to really understand our pain points, it's important to sort of put on our marketing hats and view this from a much higher level perspective, and then drill down to those details. So I'm going to steal a page out of David Allen's Getting Things Done book, where he talks about looking at objectives from like a plane landing, where it starts at 50,000 feet and works its way down to the runway, and hopefully doesn't hit it and lands nicely there. And get to the details that way. So starting right at the top, at the 50,000 foot level, what is the product? So for those who don't know, Lustre is a file system. It's a POSIX file system. So when you're writing code, you can use all those wonderful POSIX system calls to access it. It's a clustered file system that's specifically designed, initially at least, to support high-performance computing, or HPC's needs. It's open source. It runs, it's under the GPL version 2 licensing agreement. The current gatekeepers of it is my division. The group that oversees Lustre is called OpenSFS, and they've chosen us currently to be the gatekeepers, so all the code comes through us for reviews, and we land it. We are also working on getting Lustre into the upstream Linux kernel, and we have the Lustre client currently in the staging area, and hopefully someday we can get that to become part of the kernel, and then it'll appear in everybody's Linux distros, which will be fantastic. I'll be coming back to this point later in my wish list, by the way. So as the diagram shows here, when you think of HPC, we have on one side of the fabric, a large number of compute nodes, and today that could be somewhere between 10 and 100,000 nodes. On the other side of the fabric, we've got the Lustre cluster itself. Oh, and by the way, if you ever wondered, the word Lustre came from Linux and cluster, and it was put together to come up with the word Lustre. A bit of lore a lot of people don't know. Now, because it's a file system, Lustre has to store things on back-end storage of some sort, and today our limits on the amount of back-end storage units you can have is up to 4,000 of these object storage units. For redundancies, these tend to be RAID 5, RAID 6 arrays, each of these back-end storage units, and in front of them you have a series of object storage servers, or OSSs, and today we support up to 500 of these. So the ideal is that you have one storage server representing a whole series of back-end storage systems, and you change the numbers based on your performance requirements. And so we're here to talk about fabrics, and so my focus as I drill down is going to be on that little cloud in between this huge number of compute nodes and our nice little row of Lustre servers themselves. But by the numbers, just so you understand what we deal with in our job, this table was created back when we started looking at exascale, which we hope to get to by the year 2020. I don't know how accurate these numbers are anymore, but I'll go through them just to give you a feeling for things. So back in 2012, we were expecting to see in a typical HPC Lustre cluster between 10 and 100,000 nodes, but by 2020 we're hoping to grow that to be able to support 100,000 to 1 million nodes. When we start taking into account concurrency, so things like cores, so from my perspective, how many simultaneous file accesses, worst case, can I expect from this cluster? Today, we look at a concurrency of about 100,000 concurrent accesses to 1 million at any given moment in time. In the future, we need to grow that to 100 million to 1 billion. Our object create rate today is in the order of 100,000 creates per second. We need to be able to grow that to 100 million creates per second. Just jumping ahead, the file system size today, a large cluster can be 10 to 100 petabytes. I don't know if we're getting to 100 anytime soon, but we're working our way there. In the future, we were looking at saying we need to support between 600 to 3 exascale or exabytes which makes us exascale. So going right down near the bottom, looking at the really exciting stuff for fabrics, what is our expected peak I/O bandwidth today? If you start to accumulate all the bandwidth that we're using in our cluster, we expect at a peak between 1 to 2 terabytes per second of bandwidth with a sustained I/O bandwidth of 10 to 200 gigabytes per second. In the future, we need to grow that to 100 to 200 terabytes per second peak and 20 terabytes per second sustained. So very aggressive. I mean, Lustre really is exercising your fabric. So the markets, we're most known for the HPC marketplace today, and we do fairly well there. But we're also seeing enterprise uptake on Lustre as they look at things like big data with Hadoop. They're starting to look at using Lustre. We also see like oil and gas and various data analytics wanting to use Lustre. And then the last one is a bit of a new one. I'm not talking about running Lustre as a service for the cloud provider. We're talking about running Lustre as a cloud service to people who want it. So if you go to the Amazon AWS marketplace today and search for Lustre, you're going to see there is an appliance that you can check out, if that's the word you use, but you can deploy a series of Lustre services in the cloud, use them with some HPC virtual machines, and then when it's done, you can take it all down and then only pay for the amount of time and bandwidth that you used. So that's available today, and it's out there, and it's sort of a new service that's just slowly starting to gain some traction. So I put a few points here of some initial pain points when we just look at the market from a high-level perspective that we sort of have today. The first one is a hard one to describe. I wasn't sure whether I should put it here, but I'm going to take a good kick at it. As I'm watching more and more core fan-out, and what I mean by that is if you've got a node and you have a single network interface, I'm seeing more and more cores fanning out that all are competing to use that interface. And we're starting to see signs that not all those cores have the same access to that network interface because of the way that they're linked together, or the PCI bus, or what lane they're on, or we're seeing various architectural limitations that changes how file accesses work depending on which core you just happen to be on. And as Katie mentioned in her presentation, in HPC, consistency is fairly important, and this kind of thing is starting to bring an inconsistent access to our file system, which gets us a lot of support calls, from our customers. So in writing drivers or designing, the future core fan-outs, it's good if there can be a lot of consideration put into making sure that these things have equal access to the network interface itself, or even have network access to the network interface itself without a lot of weird hops around the system. I'll leave it that one as that. For enterprise, two things that are starting to bubble up to the surface. One is that they need security. With HPC, we've always assumed that these things run in warehouses with big security guards, at all the doorways, and nobody can access it from the outside. So we've never really put a lot of work into security on the Lustre side, but now that enterprise wants to use it, we have to start thinking, well, okay, now we need to worry about, access controls, does SE Linux work properly, things like that. And from the fabric's perspective, one of the requests we've got from the enterprise is, can we encrypt what goes on the wire? Now, when we're using Ethernet, we can use a VPN like IPsec to do that, but to my knowledge, there's nothing in the world of fabrics for that. So is there an appetite to create something like OFASec or some sort of, an encryption protocol that runs at the OFED level that we can then turn on and provide keys to and let it do some sort of an accelerated, encryption decryption of the fabric? Longer distances, enterprises are, almost embracing a sort of a WAN-like approach to using Lustre, and we have some customers that do longer distances, and what we have found is with some tunings, we can keep that pipe as full as possible, even though the latencies have been going up. One of the best tools we have for that is using fast memory regions. So in designing the providers, please keep this in mind that fast memory regions are important to us for helping us deal with latencies. And if you do anything to mess around with fast memory regions, at least put something in to replace it so that we can always keep those high latency links, well saturated.
50% hit if we don't.
Yeah, there's an example of someone who knows all about fast memory regions, so talk to Al if you need to know more about this particular point. And then finally, the cloud. Since we're running Lustre as a cloud service, it's running in a virtual machine. And today, it is only using Ethernet, and that's great, but we've had some feedback that these cloud providers would like to use fabrics just to improve their throughput and lower their latencies. But of course, for that to work, we need to make sure that the fabrics do support virtual machines. And I've heard in some talks here already, there's movement in this direction, and that was very encouraging to me. So that's a very good thing. So going down to the 40,000-foot view, let's take a single client and understand his relationship to that row of Lustre servers. Just wanted to point out there are actually two types of Lustre servers. One is the MDS, or metadata server, and this is a single server which handles all metadata file requests. So he stores all the metadata for the file system. Below that, we have a whole row of up to 4,000 objects, up to 500 object storage servers. Now, the way that we use these is the same way that RAID 0 works. We do striping. So we take your file, we slice it up into chunks, and we stripe them over the object storage targets. So those are we call the back-end storage systems behind the OSS's OSTs, because they're the targets. And we're a file system, we always think in terms of those hard drives, basically. And the servers just happen to be a middleman from our perspective. So if you think about RAID 0, we get the same benefits and the same problems as RAID 0. When we stripe, we get performance because we do simultaneous reads and writes to all of those OSTs. And so that gives us really good performance, especially if you stripe out to a very large number of OSTs. But we also have a problem. If you were to lose one of those OSTs, well, that's the end of your file system. So it's important when people set up Lustre that they use a lot of redundancy in their back-end storage. So they're using RAID 5 or 6, and that we also do redundancy like passive-active with the servers, which I'll point out a little bit more later, but we do support that, and that's fairly important. And we're also going to be needing to do things like redundancy with our fabric, and I'll also be pointing that out a bit later. And of course, like RAID 0, we also get capacity. So you can always dynamically add more object targets and more object servers to keep expanding your Lustre file system so that it can go up to these huge numbers that we're seeing. So a client talks to the servers by creating what we call a peer connection. And a peer connection is a RCQ pair. So we're using reliable connections today. So we create them on demand. So the first time we have to talk to a server, we create an RCQP, and we never take it down. Once we create an RCQ pair, it stays up until there's a problem or you take down your file system. We use those then to send multiple requests off to the servers. So we do parallel reads and writes by using parallel messaging across these RCQ pairs. Here's an interesting point. We monitor the health of these RCQ pairs by using something called an LNet ping. And I'm going to talk about this a bit more later, but this is a huge pain point for Lustre. A couple other interesting points. I pointed out that we only have one metadata server, but that's no longer true. As of this year, we've implemented a feature to have multiple metadata servers, and the feature is called DNE. It's not really in production yet, but it's going to be very soon, so we'll have multiple metadata servers. We also do self-imposed flow control in Lustre. Because we support multiple fabrics, we've never trusted the fabric to do flow control for us, so we do it for ourselves. Two types of flow control, to the network and to a peer. We have two tunable parameters that a sysadmin can set called credits and peer credits. Credits, it tells us how many outstanding requests we can put out to a network before we start queuing them up. Peer credits is the number of outstanding requests to a given server or a given peer connection or RCQ pair that we are allowed to put out there before we start queuing them up. And we do this because we can't have one node in the cluster monopolize the network. We need to do fair scheduling. We need to balance things out and just make sure that everybody behaves themselves and everybody has a nice, equal, consistent access to the file system. But what would be really fantastic is if the fabric will let us create a policy or a service level agreement so that we could go to the fabric and say, okay, we'll make an agreement that we won't go over the certain bandwidth per period of time, and in return, you don't drop our traffic. Because in Lustre's world, adding latency to our traffic, that's okay. But dropping our messages is really, really bad. So what we would love is to be able to say to the fabric, as long as we behave ourselves, please don't drop our traffic. Delay it, but don't drop it. If we do exceed our agreement, you're allowed to drop it because we misbehaved. And you need to protect all the nodes in the cluster. So if we had a concept of policy management or SLAs that we could create with the fabric, that would be really quite a cool thing. So going to the 30,000-foot view, getting connected, and here I want to introduce something called an LNet router. LNet is, by the way, in case you didn't catch it, is the networking layer of Lustre, and it's called Lustre networking. LNet works a lot like IP in Linux. There's a thing called IP forwarding that you turn on in Linux to make a node forward any traffic that's not destined to itself to other nodes if it can do so based on its routing table. LNet does the same thing. You can turn on LNet forwarding, and if you do turn that on and he receives traffic that is not destined to himself, he uses a routing table to see how to forward it out. And this is quite useful because you can do things like, as you see here, you can have a compute node create a single queue pair to a LNet router, send all his requests over this one queue pair, and then the LNet router creates connections to the servers on his behalf, and then funnels all the requests out to the servers that way. So a big question I always get is, well, why use routing? I mean, what's the point? And the best answer I saw was in a recent paper from Oak Ridge by Matt Ezel, where I just copied and pasted his 4 points. And so he goes through why at Oak Ridge they use a lot of routing, and namely he mentions things like controlling bandwidth, controlling the I/O paths, controlling route computation, and the last one is interesting, mixing network types. So for example, with LNet routing, you can have an LNet router bridge traffic between Ethernet and InfiniBand, between Gemini and InfiniBand, or even Ethernet and Gemini. And also, you can therefore also bridge traffic between different providers that fall under the OFED umbrella whose wire protocol aren't compatible. So we can actually move traffic between the different providers with an LNet router today. But the last point is a bit of an ask. For this to work properly, we need to have an OFED stack that works equally well on all installed network interfaces that we're using OFED to talk to. So if we have to go and build or acquire a specific OFED stack so it works best on a specific provider's card, my question is, will that work equally well on the other providers which we happen to put their cards into our LNet router? If the answer is no, that makes for a really crappy router and causes our customers a lot of angst. And also, it would be really fantastic if the providers pushed all of their best code into kernel.org so that when we do get our clients, accepted by the Linux kernel, people can run the Linux kernel out of the box from their favorite distro, and it works best for all of the different providers' hardware that you have. I mean, when the customers come to us and say, well, I would really like to rebuild with this provider's OFED stack, and we've run into all these wonderful compile problems, that creates a real bit of a support nightmare for us. And so it would be really fantastic if everything goes straight into kernel.org and then we don't have to worry about that anymore. So a bit of an ask. I think I've heard other people ask this already at the conference too, so I'll just add my voice to theirs. Just some interesting points. We find servers from the clients by using IPv4 addresses. So we use good old RDMACM calls to be able to find the actual pathways to the servers. We cannot support IPv6 for various reasons. If you want to know the ugly details, just look at the paper that I've quoted there. So we're kind of stuck in the world of IPv4 today. Our configurations are somewhat static. We do a lot of hard coding of IP addresses in the configuration. This is a problem that we have. We're not expecting the Fabric to help us solve this, but it's something we do have to address because running in the cloud, we need to conform to DHCP, and this has really been causing us a lot of angst. So this is something that we have to solve, but unfortunately it won't be too quickly. So going down to the 20,000-foot view, we've got our connection running and everything's going great. Now let's look at fault handling, like when things don't go right. In the world of HA, failover to, from active to passive is one of the most popular techniques. I represent that on the right by having two servers talking to the same back-end storage system. The clients do know about active-passive when it comes to servers, so if we lose communication with the top server, we will shift to the bottom server, and fantastic. So now we've got great HA for the servers, but what we also need to start looking at is getting proper failover when we're dealing with the fabric itself. And yesterday there was a good talk on multipath RDMA, and that's exactly what I'm asking for here, which is great. However, the problem is that we've had this request in the Lustre community for so long, somebody went and already solved it at the application level. So we call it not multipath, we call it channel bonding in the Lustre world. There is a customer who's in another week or two are going to start submitting code to our code base that does it at the module. It just sits above OFED for LNet. And the way their solution works is that we have very complicated configurations that gets pumped down to that level, and those configurations list all the servers off as a primary IP address and then a set of other IP addresses you can also communicate to that server to. When we need to set up a connection to the server, we will actually create separate RCQ pairs to each one of those addresses, and then we will do a round robin over those RCQ pairs of all our messages. So we're not load balancing connections like TCP does. We're actually load balancing messages themselves, which is in some way, from my perspective, a bit better, but it also introduces some potential problems. One of them being if a link does go down as an application, we're like the last to know, and so the chances that we're losing traffic is very high. So that's one of the unfortunates for us. But this solution has been proven on some systems by this customer, and it provides really good bandwidth, fantastic redundancy, and you can have any number of links. So if you can fill your chassis with network interfaces, you can happily load balance over all of them in a round-robin fashion. It means you can also mix fabrics supported by OFED, because their code's above OFED. You can't mix, say, InfiniBand and Ethernet, because their code is specific to OFED. But it does mean you can mix different providers and actually do load balancing over the different providers' hardware. But one of the things that we would like to have for this is to get really good feedback as to when that peer connection is in trouble, so that we can get away from it as fast as possible to minimize traffic loss. So any feedback that the fabric can give us that is starting to see a dodgy pathway, we would like to know about it as an application as soon as possible. And so continuing on with that theme, oh, go ahead.
Question about that?
Yep.
Back to that last slide.
Yep.
Can't you accomplish the same thing by putting an LNet router, take the top one just as an example, by putting two LNet routers, one on each path, and then you give it priorities and it will select between those two paths appropriately? Can you do that today? What's different here?
You can do that today, but I think in this particular scenario, the second diagram is good, is that each pathway is a completely different fabric. So one could be Mellanox and the other could be TrueScale, for example, because you decided you wanted to, spend money differently, for example. And it means that, for example, if the server's HCA card goes down, all the clients who talk to it will find out when their peer connections get flaky, and they'll flip over to the other peer connection that they created.
But again, isn't that there today with LNet? By sticking a router in? Routers?
There's still single point of failures that will wipe out all your communication, even with that scenario. And also, we don't load balance properly with routers. Like we won't, like the clients talking to the routers, that pathway, there's really no load balancing because it's still a single fabric, technically.
Well, we can divide the routers, right? So if you say we have 100 servers, then we need 100 routers more. And so those are, if you're both cost issue and then the reliability issues with those, so the complications.
The configuration is a real nightmare. Absolutely.
It gets really complicated fast.
Yeah.
It actually doesn't have some.
And also, the big ask, I think, that's in this is not so much redundancy, but it's bandwidth. I mean, people who are fanning out a lot of nodes in, a lot of cores in behind, these network interfaces want more and more network interfaces acting as a single interface so that they can, basically they want active-active, not active-passive, which was what multi-rail gives you. And so they've been looking at it and saying, well, can we get, MPRDMA, which was presented yesterday, that's what people have been asking for. And this is our...
About scaling bandwidth than it is about
Yeah, but with the side benefit that you get redundancy as well, so that if one link goes down, you just say, oh, I won't use that one anymore, but I can still use the others and everything.
requiring a router to do it.
Absolutely,
Okay.
absolutely. And it's all done at the lowest level drivers, so the file system doesn't even know this is happening. They just simply keep on happily running away, running as they will. Was there a question over here? Yes.
When you're using round robin, the link goes down, how do you recover from that? Do you retransfer the whole packet? I mean, life is good when things work, packets come nicely
Yes.
in order, you can reassemble.
Yeah. Well, I'll be getting into that in a moment, but I will say one thing, is that because we use RPC, request response, that layer will do the resend. And because if he doesn't get a response after a certain amount of time, he'll say, oh, okay, I should just resend, and away we go.
Transfer the whole,
Yeah, unfortunately, yeah. Which could cause problems. We realize that this solution has problems, and RDMA, when it's done, we will put support in for it because it might improve upon things that we've already done here. So, but my understanding is it's still coming, and so we got to do something in the meantime because the request for this is really high. I actually get almost weekly emails from some certain customers saying, are we there yet? Are we there yet? So the demand for this is really high. Like it's extremely high. So just going back to the fault handling, so we kind of need, therefore, to be able to be more reactive to when a peer connection is not in good shape. And to say that it's binary, like it's up, down, message sent, message not sent, isn't quite good enough. We would almost like sort of to see the gray areas of when there's a potential problem. So if we could be getting access to things like error counters, like resends, number of resends, number of checksum errors, like see under the covers and understand a little bit more about the health of the connection from the fabric's perspective, and then let us decide what to do. So we could have our own thresholds and say, okay, we're seeing a problem, great, we'll keep using it, but as soon as that particular error counter goes over a certain threshold that we set and make configurable, then that's it. We're going to turn off that peer connection from now, use alternatives, we'll come back to it later. That would be fantastic. And so I guess what I'm saying is that it would be great if the fabric can do more fault detection, more fault reporting, and then push some of the fault handling up to us in the application to let us make more intelligent decisions of what to do, because we don't trust the fabric to do those decisions for us. We want to do them ourselves.
Just a suggestion, S3O works great for this.
Okay.
Okay.
I will, yeah, thank you. Now, I said earlier we use pings to monitor the health of these peer connections, and this is a horrible solution, and here's why. In 2012, Cray did a good lug paper on this. They did a study and found that they lose between 4 and 11% throughput because of these pings. And to understand that, they gave an example. If you've got 25,000 clients talking to 360 OSSs backed by 4 OSTs, you're going to get 36 million pings every 75 seconds on your fabric. Well, this is horrible. This is really bad.
Number 4% on average, you lose 100% every 75 seconds for a nice big window. This goes away. It isn't like a uniform pattern.
No, it's bursty. And actually, that's true. In their slides, they showed where your data will take a huge hit. It drops and then comes back again. So you get these ugly, blackout periods. Thank you. That was a very good point. You get these blackout periods when we do this. And so there's a lot of work we could do, but ultimately what we need to do and should do is to create a brand new health network based on a protocol like Gossip, which lowers the packet counts by quite a bit and gives better scalability. And we will do this since this is in our plans, but what would really be great from a fabric perspective is if we could get high priority messaging for these things, because we don't want to lose our health packets. We need them to take precedence over everything else, and jump ahead of queues and switches, things like that. So if we could get high priority messaging, that would be fantastic to help us out. The last point, go ahead.
Are the pings then using the same RDMA channel that's
Yes. Yes.
So, I mean, we can do it at different service level, and so we do that for certain things in our configuration.
And that,
basically, we need another queue pair, so if you could do that, then we can establish.
Yes.
Where it's working.
and I think in another slide or two, I'll point out, we have so many queue pairs, we're trying to avoid creating too many, but that would be a potential solution, certainly. Now, the last point is one that a lot of people don't know, and I wanted to point it out. Oh, question over here?
Two questions. This health monitoring is from which node to the which node?
Oh, it's from the client to every single queue pair it creates to the servers.
So if there is an active traffic, why do we need to do health monitoring? Because the active traffic on the same system has
Yeah. That's a good question. Yeah, unfortunately, there's a lot of history in this, but one of the things, if you were paying attention, you'll notice that we multiplied times the 4 OSTs, and you're thinking, well, why are you pinging a hard drive? You should be pinging only the OSS. It turns out that the pinging is done by the Lustre file system, and the Lustre file system knows nothing about the network. It just thinks about hard drives. So it literally is pinging the hard drive to figure out the health of the hard drive. So these pings are also trying to figure out whether the hard drive or the disk array is in good shape or not, so to get the health information about that. Now, we definitely can do better at that. I mean, that extra multiplier times 4 we shouldn't have had to do, but unfortunately today we do. And the reason also is in the case of failover, we don't know what OSS we're going through for that particular OST. So we have to ping the OST and let our routing algorithms figure out how to get to the OST, so which OSS we go to, so that if we do fail over, we still are able to figure out the shape of the hard drive. So, go ahead.
So can we test that to health monitoring, the server in the backend does its own hardware monitoring?
This is what we want to do. And so when I mentioned creating a proper health network, this is what we're talking about. And so it's a lot of work, but we know we have to do it because as we move towards exascale, this is not going to work. We can't have that 36 million turning into 36 billion every 75 seconds. That's absolutely not acceptable. The last point, again, a lot of people in the fabric world don't get, and I want to point it out. Lustre doesn't care about ordering. We are RPC based. Every file access is a request, and we wait for the response to come back before we do anything else. So for us, if things get reordered, we really don't care. And so that kind of frees us up of a lot of fault and error handling in our own code. And so from our perspective, we don't care. Now, if the fabric tries to keep things in order, great, that's fantastic. But you don't have to do it for our behalf. We really don't need that.
What's the penalty you paid for bonus?
In terms of that, it's not too bad because remember, we're trying to get consistency. We're spreading, our use of the fabric out over all the clients. And so this is an extra bit of flow control as we sort of, request, response. But the fact that we're doing very wide striping, like you could stripe a single file over 2,000 OSTs, worst case. So you can literally stripe over so many, and you're doing so many parallel read operations to get that file. The performance is still very good. So going down to the 10,000 foot view, the stack itself. At the very top is the last component of Lustre before we start talking to the networking layer, and that's called Portal RPC, and as the name implies, he creates and processes all the RPC messages, so the outgoing requests, the incoming responses. Those go down to the LNet module, and so these are actually all are kernel modules. So all of the stuff runs in the kernel, and I guess that's another point I should make. Lustre, or at least these parts that we're talking about, are all kernel modules, and so we have to use kernel API calls. We're not in user space. We're not using lib anything. We are down in the kernel space. If you as a provider do something and you don't support kernel space, you only support user space, you've just killed Lustre. So I just wanted to point that out. So LNet runs as a module with all the common networking code, and then below it, the next level, are what we call LNDs, or LNet network drivers. And these contain fabric-specific code that we need to use so that we can support that fabric. And the three most popular fabrics we support today are, Craze Gemini, Ethernet, which is basically just TCP over IP over Ethernet. And then with the O2 IBLND, we support OFED, and with that, we therefore support all the providers below OFED. So technically, if you create a provider, and as long as you support all the kernel calls for OFED for that particular provider, in theory, we should work with your fabric. We may need to do some tuning with buffers and stuff, but we should work just fine. Over here first, I guess.
Your health involves the kernel?
Yeah.
Okay, so that's why it's so good.
Yes.
So that's why it's 4% or 30%. So that's something that you could actually make really, really efficient, because you don't care about the exceptions.
Exactly.
That call down the user space. So what you really do is
which we should start to, we've kind of been ignoring user space, but I think it's time to embrace.
just for the pure health piece.
Exactly, like the administration courses. Yeah.
Modest, right? It's 36 million interrupts it is.
Yeah. Yeah, I absolutely agree with that. Question over here?
You said in theory it supports all the providers. Have you done any testing of anything other than IP?
Interesting you should say that. I believe a customer has, but we haven't, and that's kind of the problem, is because we haven't done it, we haven't verified it, but there has been talk that in theory this works. But how well is always the question. A lot of these things will work, but when we try them, we always find, oh, gee, we need to change the way we use buffers, we need to introduce the better use of FMR. We always find there's some tunings we have to do, and so as a fabric, anything you can do to make this work black box style for us would be really appreciated, because right now we do have to do we have to spend about 2 or 3 weeks doing validation testing and tuning to get the best out of each fabric. And then we have to find some way to let the customers know about this so that they can set up all these tuning parameters.
But you haven't gotten the Rocky yet.
No. But a lot of times we just do based on customer requests, and we haven't had one for this yet. But if we ever get one, we'll try it. Because our cluster keeps getting bigger and bigger and more expensive, and so this is a very arduous task. So from an OFED usage point of view, 3 things that are quite interesting for everybody here to know. One is we only use puts. And that means that we only do RDMA writes. We do no RDMA reads from our LND. Why did that happen? Well, it turned out that when we were writing the LND, the developers were told that there's no limitations on the use of RDMA writes, but there are limitations on the use of RDMA reads. I think that scared them, and they turned around and said, well, let's just use RDMA writes for everything so that we don't run into any limitations. And that's the history of that. Ultimately, it would be fantastic if we could use gets or puts as appropriate. Because today, if we have to do puts for everything, there are scenarios where we have to do this extra handshake with the other side to trigger the RDMA write. We'd love to get rid of that. And so if we could use interchangeably do RDMA reads and writes, that would be great. But before we could embrace RDMA reads, we need to understand this limitation. And that could be done in two ways. One, if it's an adjustable thing, we would love to have controls so we can set what those limitations are and control it so it matches up with our flow control parameters. Or if we can't change it, at least can we query what these limitations are so we understand them and make sure that our flow control helps us from running into this limitation. Because I guess the point is we don't trust what's going to happen when we run into these brick walls with the fabric, and so we want our flow control to take precedence over whatever the fabric may do to us. Because again, packet loss or message loss for us is really bad, and we want to avoid it where possible. So we want to do our own buffering and add latency. So if there was a way for us to query the RDMA read limitations, that would be really fantastic. We, as I pointed out, use reliable connections, and that, of course, uses a lot of resources. But because ordering doesn't really matter to us, we would love to use reliable datagrams. I mean, if we can just use datagrams to cut down, the overhead, that would be fantastic. And then the last point I just put there just so that people understand a little bit better how we operate. When our networking layer gets a message or a request or something that we have to do, if it's less than 4 kilobytes, we use immediate messaging. If it's more than 4 kilobytes, we use an RDMA write. We do not use atomics, and of course, I've already said we don't use RDMA reads. So that's our pattern. That's how we do things. We'd like to change some of it, but that's what we're with today as we stand here. And last, we're now on the runway. I'm not going to go through this, but I provided it for anyone who downloads the slides. In O2 IBLND, these are all the function calls we make to OFED. So if you break one of these, you break Lustre. If you break something that's not on this list, you don't break us. It's fine. Go ahead.
FMR, in-advance specific.
Which one? The
FMR?
I believe it is, yes.
So that means it wouldn't work over IWAR.
Well, we don't support iWarp anyways, but yeah, that's true, yeah. Yeah. So anyways, that's our list of APIs. You can download the slides and look at them if this really interests you, but that's basically all we do with OFED today. And the last two slides are the asks that I mentioned. So again, you can download the slides to look at those, my little summary of 10 things that we've asked for. And that's basically it. Any questions?